Hello, am I audible?
Yes, sir.
And my screen is visible, right?
Yes, sir.
Okay, so welcome everyone to the week 9 discussion of this course, Introduction to Machine Learning. And myself, Ayan Paul, I'm a PMRF research scholar from IIT Kharagpur, and this course was originally taken by Professor Balaraman Ravindran, Professor and Head of the Department of Data Science and Artificial Intelligence, IIT Madras. So, like we did in the previous class, what we will do, we will discuss some of the concepts related to this week's lecture, and then we will solve some question that will be the base for your for solving the assignment for this week. Okay. Okay. So yeah. So last week we have discussed about Bayesian network. Okay. So Bayesian network, what I have told, Bayesian network is a DAG. What is a DAG? DAG is directed acyclic graph. Okay. So according to graph theory, like directed acyclic graph, there is another category of graph known as undirected graph. Okay. So two categories. One is directed graph, and the category is undirected graph. So we will see this in today's lecture. Okay. So graph theory, it is a branch of mathematics that deals with study of graphs, and it consists of a set of vertices, nodes connected by edges. Okay, someone is joining. Okay. So again, I'm repeating. What is a graph theory? A branch of mathematics that deals with study of graphs, and it consists of set of vertices, nodes connected by edges that you have all seen in that Bayesian network. Okay, let me just 1 minute. Okay, someone is joining. Okay. So yeah, so last week what we have discussed about Bayesian network. So Bayesian network is a DAG, that is directed acyclic graph. Okay. So directed graph, we know something about directed graph. So today we will focus mainly about undirected graph, and we will see the difference between this directed and undirected graph. Okay, so graph theory, it consists of set of it consists of it is basically the study of graph. And what is a graph in this graph theory? It consists of set of vertices nodes connected by edges that we have seen in our Bayesian network, that is directed acyclic graph. Now again, a directed acyclic graph, a directed graph is a graph that is unidirectional. In this, the edges have a specific direction, and the edges have direction specified with them, like we have seen in the like we have seen in our DAG. This is a directed graph. Directed graph means, see, we have node, and this is known as edges. These nodes are also known as vertices, or these nodes are also known as these nodes are also known as vertices, and this is known as edges or links. Okay, so in directed graph, these two nodes, like any two nodes, are connected towards each other, to each other, and it is connected by a edge, and this edge has a particular direction. That is, it is an unidirectional. That means this edge has a particular direction. That means one is linked with two, but the arrow is from 1 to 2. That means 2 is a child of 1, or 1 is the parent of 2, like that. So that is the concept of directed graph. Directed graph, it has ordered pair of vertices. Again, I have told you that these nodes are also known as vertices, and these edges are also known as links. Okay, so in this directed graph, we have ordered pair of vertices. That means when we will write our directed graph, like G denotes for graph, and V denotes for vertices, and E denotes for edge. So basically, we want to have the relationship between different nodes or different vertices with the function of edges and vertices. So 1 2, whenever we are writing 1 2, okay, someone is joining. Yeah. So whenever we will write our directed graph, we will write in this form. That is 1 2, then 2 3, yeah, then 3 4, then 4 5, and then 5 1. Okay, and also these two are connected, so 1 3. Okay, now in this we cannot write 1 2 as 2 1. So this is the property of directed graph, that it contains asymmetry. Okay, these are not symmetrical. This relationship or this links are not symmetrical, these are asymmetrical. That means 1 2 is not equal to 2 1, because there is a direction of node 1 with respect to node 2, or 2 is a child of node 1, or 1 is the parent of child 2. Okay, so we cannot write the opposite, like 1 2 we cannot write as 2 1. So this is the property of directed graph. The applications of directed graph: Bayesian network, that we have seen; transportation networks, like your product is prepared in a factory, then it goes to the consumer. So the network in between, that is also an example of directed graph. That means the goods will go from factory to the consumers, not the other way. Not the goods will not go from this consumers to the factory. Okay, so that is why this type of relationship, or this type of graph is a directed graph, and transportation network is an example of a directed graph. Now about undirected graph. An undirected graph is a graph where the edge do not have a specific direction, and it is bidirectional in nature. It does not have a parent-child relationship concept, and there is no particular direction. Okay, here also we have nodes, here also we have links or edges, or nodes or vertices, same thing. Okay, graph theory, the graph consists of this vertices or nodes, and edges or links. Okay, So it is both for directed as well as undirected graph. The only difference is how the edges are in a directed and undirected graph. In directed graph, the edges has a particular direction, it is unidirectional, but in undirected graph it is bidirectional, or edges do not have a particular direction. That means now when we are writing our graph GVE, that is vertices and edges, we will write, okay, someone is joining. Yeah. So now this time when we will write, okay, write our undirected graph, we will write in this form. Okay, so you can see the difference in this and this, as this is ordered pair of vertices, so you can particularly see 1 comma 2 and 1 comma 2 written in first bracket, but 1 comma 6 is written in second bracket, as it is unordered pair of vertices. Now this undirected graph, alike from directed graph, it holds symmetry. That means 1 6 can be written as 6 comma 1, because it does not have direction, right? Here we have to write 1 2 only, because node 1 is connected to node 2, but here we cannot write here we cannot write 1 2 as 2 1, but here we can write 1 6 as 6 1. So undirected graph holds the property of symmetry. Okay, now notation, how to write notation of directed graph. When A is connected to B, or when 1 is connected to 2, we can write 1 directed to 2. Okay, 1 directed to 2. Okay, but here we will just write 1 comma 2. So this is the difference of notation between directed and undirected graph. Now what is the application of this type of graph? One is social network, like your Facebook or any social media apps. So in social media apps, when we when our friends, okay, yeah, when we are being friends with someone, what we do, we can communicate, or we can send messages both the ways. Means you can also send message to your friends, your friend can also send message to you. So social network is a type of undirected graph. Now communication network, like when you are just calling your friend, or any type of other communication networks also. So this is particularly an example of undirected graph, because the message or the transfer of message is bi-directional. Okay, so but like a communication, like you can say, like there are some emails that in below of that is written, you cannot reply to that emails. That type of communication is an example of directed graph. Okay, so is this slide clear to you all? What is a
Yes, sir.
directed graph, what is an undirected graph? Clear, right?
Yes, sir.
Okay. Now now why we are reading this particularly undirected graph? Because one of the problems of that Bayesian network that we have discussed is acyclicity of that network. What is that acyclicity? I have told you Bayesian network is a DAG, okay, directed acyclic graph. That means it cannot form loop. Okay, now say this example, if we will solve with our Bayesian network, what will happen is, like, see, B is the child of A. Okay, C is the child of B. Now A is also the child of A. Okay, again I am telling, B is the child of A, C is the child of B. Now A is also child of C. So that is not possible, right? So whenever we are writing this Bayesian network, I have told you Bayesian network, it depends on conditional probability with respect to parents. Okay, you have marginal probability for parent, and then conditional probability for child. Okay, the conditional probability for a child depends on marginal probability of the parent. Okay, so A B C, or probability of that system, we can write probability of B given A, because A is the parent of B. Then probability of C given B, because C is the child of because B is the parent of C. Now probability of A given C, because C is the parent of A. Now this does not make sense. Okay, this does not make sense. This only makes sense if probability is 1 for all, because this is the problem of cyclicity. But Bayesian network always solve our acyclic problem, because now what is happening is B is the child of A, but B is the child of A, C is the child of B. Now A is also the child of C. So that is something illogical. Okay, so this is the problem of our Bayesian network. Okay, now to deal with that, we have come across with this Markov random field. What is a Markov random field, or MRF? It is similar to our Bayesian network in its representation of dependency. The only difference being Bayesian network are directed and acyclic, whereas our Markov network are undirected and maybe cyclic. Okay, the cyclic problem can be solved by our Markov random field. Thus, a Markov network can represent certain dependencies that a Bayesian network cannot, such as cyclic dependency that we have discussed here. Okay, so Markov property, there is a particular property of this Markov random field that is known as Markov blanket. A random variable in a Markov random field is conditionally independent of all other variable given its neighbor. Okay, the variables directly connected to it. Neighbor means, Markov neighbor means the variables that are connected to the nodes are known as Markov neighbors. Okay, so for a random variable xi in Markov random field, we write pxi pxi given x others equals to pxi given neighbors. Okay, so that is the property of Markov random field. Okay, so this slide you just remember this thing, that a Markov random field is similar to a Bayesian network. Only thing is it also solve undirected problem as well as a cyclic problem. Okay, and it is very similar to our Bayesian network. Now Markov random field has a property such that a random variable in a Markov random field is conditionally independent of all other variables given its neighbor. So if neighbors are given of that particular nodes, all other nodes are independent of that node. Okay, so we can discuss in the next slides, and this is a property of a Markov random field, like for that Bayesian network, what we have discussed is Pxi given parents equal to given all other P probability of the system equal to probability of this xi given parents. Okay, given the parents. So that is a property of Bayesian network. But this is the property of random field, because here our node is directly dependent to his neighbor. Okay, here there is no there is no concept of that parent child relationship, but here is a concept of neighbor relationship. Okay, so so the dependency of all the there is a direct dependency of all the nodes with respect to its neighbors. Okay, so this is the property, this property is known as Markov property. Okay, so is it clear? Okay, is it clear?
Yes, sir.
Okay, so we will better discuss in the question, so that will be more clear to you. Okay, so factorization comparison in the Bayesian and undirected. Okay, someone is joining. Yeah, so factorization comparison in Bayesian and undirected graph. So Bayesian network and Markov random field. Okay, so joint probability factorization that we have seen in our Bayesian network, that is this probability of the system equal to multiplication of probability of each node with respect to its parents. Okay, given its parents. Okay, So this is the factorization rule or our chain rule for our Bayesian network. Similarly, for our random Markov random field, we have this factorization thing. Okay, so probability of the system equal to 1 by z into 1 by z into this phi c is a phi c is a potential function, okay, or it is known as click potential of all the clicks, okay. So again I am telling, here it is multiplication of each node with respect to its parents, okay. Here it is multiplication of each clicks, okay. What is a click? Click is a subgraph of a click is a subgraph, and it is used for this directed graphs, okay. So we will again see what is a click. So yeah, 5 and there is a z term also, okay, 1 by z. So 1 by z, what is this z? Z is normalizing constant, also called as potential function, to ensure that probabilities sum up to 1, okay. This is the thing. So again I am repeating, like Bayesian network, the probability of the system is calculated by probability of each node given its parents, okay. Multiplication of probability of each node given its parents. Here it is multiplication of each click potential, okay. Multiplication of each click potential. Now what is a click? Multiplication of each click potential and divided by z. What is z? Z is a normalizing constant, because probability should be less than 1, less than or equal to 1, okay. So for that we are normalizing the thing, that is why we are dividing by z, okay. And click is a subgraph of the directed graph, okay. So this two is the difference of factorization between our Bayesian network and our Markov random field. Now this is the example of factorization in Markov random field. Here you can see a Markov random field or a directed graph, okay. So these are the nodes A, B, C, D and E, and these are the connection of the nodes, okay. Okay, someone is joining. Yeah, these are the connection between the nodes. Now probability, what I have told you, probability here we will write in terms of our click potential function, okay. Click potential function, click function is denoted by phi, okay. So phi, what are the different clicks or subgraph we can construct? One subgraph is AB we can construct, one subgraph is BC we can construct, and the one is BD we can construct, BE we can construct, and CE we can construct. Anything left? AB, BC, CD, and BD and DE. So five subgraphs or five clicks we can construct. Now how we will calculate our probability? The probability will be 1 by z into potential into 1 by z into multiplication of all the click potential, okay. So click potential of AB into click potential of this BC, click potential of BD, DE, CE, and anything left? AB, BC, AB, BC, BD, DE and CE, okay. So that is how we will write our probability, okay. If it is a Bayesian network, how we will write our probability? First, it will not be cyclic, and how we will write our probability? We will write our probability with respect to its parents, okay. So like if this is the thing A, B, C, and let's say DE. Now how we will write it? First we will write marginal probability of A, okay, into probability of B with probability of B given A, similarly probability of C given A, okay. Then probability of D given B, and probability of E given B, okay. So by that we can write our probability in case of Bayesian network, but here we will write our probability by this, okay. So this is the difference between our difference of factorization between our Bayesian network and this Markov random field. Okay. Now another example, as it is a directed graph, so it can be joined or it can be created cyclic from anywhere. So if we join D and C, now how we can build our clicks? We can build our clicks as AB. Okay. Then BCD, BCD, and then CDE. Okay, CDE. So we can make three clicks or three subgraph, and then again we will write our probability in terms of this potential function. Okay, click
Can
potential function.
we,
Yeah, please.
sorry, can we make ABD also?
ABD. Okay, ABD. ABD. Yes, you can make ABD. But then ABD, if you will make, then you can make this BC and then DEC. Okay,
Okay.
Sir,
ABD.
actually,
Yeah, yeah,
sir,
please.
this is an undirected graph, sir, we
Yes,
have
yes,
taken.
yes.
So, in this notation, yeah, B comma D is there, no? Why can't it is D comma B? Because it's an undirected, it's as told, it's a bidirectional. So, B comma D means once again D comma B is also holds good, no, sir?
D
It's an
comma.
undirected
Yeah,
graph.
yeah, yeah. You can write D comma B also. No problem.
And why can't we only two no means two edges, two nodes we have to take for our clicks, sir? A, B like B, C and C, E and D you told.
No.
Can't we take four nodes at a time?
Yeah, yeah. You
Like
can take.
a
You can take.
triangle
You can
or
take four nodes at a time. But what is the
rectangle.
concept of factorization is how much small you can break it into. Okay.
Okay, okay,
So that is the
okay,
concept of factorization. So
okay,
that is why we are breaking as much smaller nodes as possible,
okay,
as much smaller clicks as possible. Okay.
okay, okay, sir.
So this is about factorization comparison in this Bayesian and Markov random field. Now connectivity in Markov random field, any two subset S and T. Okay, any two subset S and T of variables are conditionally independent given a separating subset, or we can simplify by this: all parts between S and T must travel through separating subset. Okay, so this is the property of Markov random field. So this is basically the property of Markov random field, or Markov property: a random variable in a MRF is conditionally independent of all other variable given its neighbor. Okay, so if its neighbor is given, then it is independent of all other it is independent of all other nodes. Okay, so what does this connectivity tool, like you see this. Okay, like you see this. So A has how many neighbors? A has only one neighbor. So if I give B, then A is independent of C, D and E. Okay, if B is given, then A is independent of C, D and E. Now what about B? If if all is neighbor of B is given, that is A is also given, D is also given, and C is also given, then B and E are independent. Okay, so this is the concept of Markov random field. That is, you can tell that if a node is given, so let's say that if a node is given for B, if a node is given, like D is given. Okay, but we have to find the independence of B and C. So B and C can still be traveled. If I block D, if D is given, that means D is blocked. If I block D, then also the path can be traveled from B to C. So B to C are not independent. Okay, so this is the connectivity rule of Markov random field. So very simplified way I have told. So again I am repeating. No need to focus on the language here. Just focus on this. Like A, what are the neighbors of A? Neighbors of A are B. So if B is given, so this is blocked, right? So if the neighbor is blocked, then no path can be traveled from A to D, E or C, right? No path can be traveled, because to travel from A to C, E or D, you have to travel through B. So if neighbor is given or this B is blocked, then you cannot travel to C, E or D. In that case, A and D, E and C are independent. Okay, this is the concept of and this is also known as Markov property. Now what about B? B has three neighbors. Okay, A is a neighbor, D is a neighbor and C is a neighbor. If A is also given, D is also given and C is also given, then this B and then there can be a connection between. Okay, let me erase it. Okay, so if for this B, let's focus on this B node. Okay, so for B, what are the neighbors? This A is a neighbor, this C is a neighbor, this D is a neighbor. Now if all the neighbors are given, this is also given, that means this is blocked. C is given means this is blocked, D is given means this is blocked. Now if all the neighbors are given, then this B and E are independent. Okay, but let's say that D is not given. Okay, D is not given. D is not given, and C is given as well as A is given. Now what is the dependency of B and E? Okay, okay, Suma, any doubt? Any doubt, Suma? You are raising hand. Any doubt? Okay, no doubt, I think. Okay, so what I was telling is, for B, if this A is given and C is given, now what about the independency of B and E? This B and E are not independent because the path can be traveled from B to E. By via D we can travel the path from B to E. So B and E are dependent if A and C is only given and D is not given. Okay, so this is the rule that is derived from our Markov property. Any doubt regarding this? Should I repeat again? Any doubt?
So,
Yeah, please.
uh, the travel can be done only through the connection, right?
Yeah,
Even if we block the some other
travel can
nodes.
only be done through connection only.
Okay. So, unless or otherwise, if D is not blocked, it can be traveled through B to D, B, D, and D. If A and C are blocked, right?
Yeah, for that B, if A and C are blocked, okay, A and C are blocked, and we need to find the dependency or independency of BE. So B and E
B.
in this case is dependent. Okay, not
Okay.
independent but dependent. Why? Because path can be traveled from B to E via D. D is not blocked, so path can be traveled from B to E. So B and E are dependent in that case. But if
So,
all the
yeah.
neighbors, what Markov property told, if all the neighbors are given, what happened is this D is also blocked. Because what are the neighbors of B? This is the neighbor of B, this is the neighbor of B, and this is the neighbor of B. Okay, so if all the neighbors are blocked according to our Markov property, so this B and E will be independent because you cannot travel to B to E, because here if you travel via this path, this is blocked. If you travel via this path, this is blocked, so you cannot travel from B to E. Okay, so B and E are indi B and E are independent if all the neighboring nodes are given. So this is Markov property. Okay,
Sir, if I block E, then what happens? Only B is an independent.
yeah, if you block E, okay, if you block E also, then what is the relation you want to derive? Between what you want to derive your relation?
To traverse from A to E.
A to E, A to E. Okay, so A is not blocked, right? A to E, you want to traverse your
Traverse.
direction. Yeah, okay, let me erase this. Now what will happen is A to E. So you are comparing A to E. B is not blocked or B is blocked? B is not blocked, then you can travel from A to E. Okay, okay, A to E, right? You cannot you can travel from A to E if B is not blocked. If B is blocked, then what will happen is you cannot travel from A to E. There is no path to travel because you have blocked this you have blocked this neighbor, so you cannot travel from A to E. So A to E are independent if B is given. A to E is
Then
given.
A, C, E are independent.
Yeah, Now what you are telling, if let's block D, okay, let's block
Mm.
another
Mm.
node D, then we can
Mm.
travel from A to E, A to B to
Yes,
C, then
yes,
to E, then we
yes,
can travel.
yes.
And if we block this two, okay, if we block this two, then what will happen, we cannot travel from A
We
to E.
can't. Then
Okay.
A, B, E are the
Yeah,
independent.
yeah. So this
Yes,
is
sir.
the concept. So is it clear to all the class?
Yes, sir.
But if we are blocking A, C, and D, sorry,
If you are
A,
blocking,
C, and D, if
yeah,
you are
if
blocking A, C, and D,
yeah, C and D,
then we can't go to E, right?
no, you can't
So
go to E.
A, yeah, A and E are independent, but A and B are dependent, right?
If you cannot travel from A to E, so
Then
A and E are
A and E are
independent.
independent. A to B is dependent, right? In this
A to
case.
B is dependent because
Okay.
you can travel, but A to E is independent.
Okay. May I know what is the significance of finding the dependent or independent, if you don't mind?
This is all related to your transferring message, like we are forming a network here, right? So this is all
Okay.
related to passing message from one node to another node. So you have to
Okay.
know the dependency, like like
Okay.
we everything we are doing to calculate a marginal probability with respect to another node. Okay.
Okay.
So
Okay.
like marginal probability, if we want to calculate with another node, we have to know the path in between. Path is blocked or path is not blocked. Okay. Because
Okay.
here if we get the evidence here, like there are two things. Okay. This is the marginal probability, and this is the conditional probability, A with respect to some, let's say, X. Okay, this is the conditional probability. So generally what we want to do, we want to know the this probability or the conditional probability given a marginal probability. Now if we do not know the path in between this A and X, then what we will do, our evidence will not transfer. This is known as prior probability or the evidence. Okay, so this evidence will not sorry, X with respect to A, sorry, this is reverse, this is okay.
Okay. Okay. Thanks.
Okay, so this is X. Okay, so this is X with respect to A. So yeah, so this is the evidence, right? This is the evidence, or this is the prior probability. This is the final thing, or this is the posterior probability. So until we do not know the path in between A and X, we cannot find the conditional probability. Even if we know the marginal probability, we cannot find the conditional probability. Okay, so that is the
Okay.
significance. Okay.
Okay. Fine.
Now Bayesian network is MRF. Okay, anyone any doubt regarding this? This is a very fine concept. Any doubt regarding this, you can again ask.
Sir,
Anybody? Yeah,
just now we explained regarding about factorization, right, sir?
yeah,
Clicks.
yeah, yeah,
Means we need to create the subdrafts.
yeah, yeah.
Please, can you explain with an example how we can calculate the size of that factorization, sir? That formula you told, no, 1 by z, pi of that.
Yeah, yeah. 1 by Z. Yeah, yeah. This.
Yeah, 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 sir.
Yeah. So what is your doubt exactly?
So how we can find out the factorization in this graph?
Factorization is this. This is the example, and this is the factorization.
The formula, what is the usage of this formula?
Formula,
P of x1
you have to multiply
equal
the
to,
click potential of all the clicks. Okay. Okay, so you are telling about a numerical example on this.
yes, 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 yes.
Okay, so next class I can include that.
Okay, okay, sir.
Yeah.
Okay, sir, sure.
So yeah. So now Bayesian network is MRF. Okay. Now can we convert our Bayesian network to MRF? So that is the topic here. So you can see this is a Bayesian network. A to A is a parent and B is a child. Okay. So to convert this, we have just excluded this link, and we have directly connected A and B. Okay, so probability, if we are to write as a Bayesian network, then we will write like this: probability of the system equal to marginal probability of A into conditional probability of B given A, because A is the parent of B. Okay. Now what about our what about this case? If we are converting it into a directed graph, then probability of a comma b, that will be proportional to, because we cannot write here equal to, because 1 by z is also there. That is why we are writing proportional to phi a b. That means potential function of click a b, because we can only form one click here, so that is why a b. So converting a single hash to a pairwise click potential is easy. Okay. Now what about this case? That is B is a child of A and C is a child of B. Okay. Now how we can find out our probability by Bayesian network? That is probability of A comma B comma C, that will be equal to marginal probability of A, conditional probability of B given A, now conditional probability of C given B. Okay. Now if we convert this into a directed graph, that is A linked to B, B linked to C, then probability of A B C, okay, some disturbance is coming. Yeah. So probability of A B C, that will be proportional to our multiplication of potential function of clicks. Okay, so two clicks here we can form A B and B C. So phi A B, that is potential function of click A B and potential function of click B C. Okay, so that is how we can convert our Bayesian network to this MRF, or Markov random field. Now this this phi AB will be dependent on probability of A given probability of B given A, because that is how the masses will travel, because the masses will travel from B to A also, so A to B also. That is why probability of A, that is, you can say this is an analogy of this Bayesian network with respect to Markov random field. So clicks we have written like this, but if we want to show it like a probability, so that will be equal to probability of A into probability of B given A, and BC, that will be equal to probability of C given B. So it is nothing but it is just an analogy. Okay. Now about the third case, that is A is a parent of both B and C. Now how we will write probability of ABC? That probability of A, then probability of B given A, and probability of C given A, because A is the parent of child B as well as A is the parent of C. Now about this, if we convert this graph into a Markov random field or a directed graph, we can write our probability as a proportional to the product of the potential function. Here also we can create two clicks, one is AB and another one is AC. Again we can draw an analogy between the probability and this potential function. Okay, but this case, when we have two parents and we have one child, here there is a problem. What is the problem here? Here if we write our here you see the dependence. Okay, if we see the dependence, then here if here according to our explaining away effect, if C is given, then A and B are dependent. Okay, A and B are dependent if C is given. That is the third rule, or the explaining away effect in our Bayesian network, you might remember. But here if we talk about independency, if we do not have this line, so what will happen is A, C and B, right? Now what will happen is, if C is given according to our Markov random field, if neighbor is given, then A and B are independent. So here this is a problem. Okay, again background noise coming. Okay. Yeah, so this is the problem. Okay, again I am repeating, in this two case there is no problem of the relation. If the middle node is given, then what will happen is these two nodes are dependent. Again here also, if middle node is given, these two nodes are independent. Okay, this Markov random field, and this is we have discussed in Bayesian network also, same thing. Here also, if middle node is given, that is A is given, that means B and C are independent. Like our Bayesian network, here also if A is given in Markov random field, if neighbor is given, then the nodes are independent. Okay, so these two cases hold, but when we have this third case, that is we have two parents and one child, what will happen is, in our Bayesian network, what we have observed, if the middle node is given, then these two nodes are if the middle node is given, these two nodes are dependent. Okay, that is according to our Bayesian network, that is third case, or explaining away effect. Okay. Okay. Now, in this case, if we convert this into a if we convert this into our this thing, that is Markov random field, what will happen is, in Markov rule we know, if neighbor is given, then the nodes are independent. But this is completely analogical. This is completely the reverse for or the contradiction is happening if we compare our this Bayesian network with this Markov random field. So for that, this what we will do is, we will apply a concept called moralizing parents. When we are applying this concept of moralizing parents, what will happen is, we will join the parents, that is we will join A and B. So when we will join
Excuse me.
yeah, please.
No, here in the second case, that is MRF,
Yeah,
suppose C is given.
yeah, yeah.
We had drawn a blue line between A and B.
Yeah, that is known as moralizing the parents, because
Okay, okay.
here that is the dependency and independency analogy, contradiction between our Bayesian network and our Markov random field. If this blue
Oh,
line is not given, what will happen is, if C is given, then A and B are independent according to Markov rule. But according to
okay.
Bayesian network, if C is given, A and B are dependent
Depend. Yeah.
according to our Bayesian network. So there is a analogy. So that is why we apply this concept called moralizing the parents. If such case happen, what we will do? We will connect the parents, or we will moralize the parents. So when we will moralize the parents, we have three clicks, that is AC, BC and AB. So by AC, BC and AB. Okay, so by that we can write our probability. Okay, so moralizing parents means we will moralizing the co-parents, but the problem here is, if we will moralize the parents, we will lose the marginal independency of the parents. Okay, so the parents should be marginal independent, but if we will join this, we will lose the marginal independence of the parents. So by this we draw a conclusion that directed graph and undirected graph, if we will compare with the help of pie charts, or you can say a flow diagram, what we will see is yeah, there are some cases in which directed graph and undirected graph, the relationship between this directed and undirected graph will be same, but there are some cases in which the relationship of directed graph does not hold to the relationship of an undirected graph. Okay, is it
Sir,
clear?
please can you tell me once again how A and B is independent on given C, that shared child?
A and B is independent given C. Okay, so A and B, like Markov random field, this is the property of Markov random field, right? A random field in a MRF is conditionally independent of all other variable given its neighbor. Okay, so given its neighbor, if A, I have, what is the neighbor of, if this blue line is not there, what is the neighbor of A? We have only one neighbor of A, that is
B,
C.
B and C.
Not B. If this blue line is not given, let's say this
Ah,
blue line is not given, so so what is the neighbor of A? Neighbor of A, if A is only C. Now if
C.
C is given, that is we are blocking the C, then A and B are independent. Okay, so that is why A and B is independent according to our Markov random field given C.
Okay.
Okay, but this concept does not hold in the case of Bayesian network. Bayesian network, we have seen three effects, right? So first two effects are this effect and this effect, this effect and this effect. Okay, and third effect is this effect. Okay, so this effect, it is also known as explaining away effect. So in explaining away effect, what we have seen is, if the child is given, that means the co-parents are dependent. Okay, not independent, but co-parents are dependent. So this is according to our Bayesian network. So to solve this analogy, we apply this concept of moralizing the parents, that is we join the parents. So whenever we join the parents, but by this we lose the marginal dependency of the parents. So in conclusion, we can say this directed graph and undirected graph, there are many relationship in common, but there are some relationship that is not common. Okay. Now yeah, so is it clear?
Yes, sir.
Okay. Now let's move on to the next topic called belief propagation. So belief propagation, also known as some product message passing, so it is related to passing of message, is a message passing algorithm for performing inference on graphical models such as our Bayesian networks and Markov random fields. So it calculates the marginal distribution for each unobserved node or variable condition on any observed nodes or variables. Okay, nodes or variables or edges or vertices, whatever you told. So this is about belief propagation network. So again I am repeating, belief propagation, also known as some product message passing. So it is a message passing algorithm. Okay, so how does it pass your message? By some as well as producting the message. How it is passing, we will see. So it is a message passing algorithm for performing inference on graphical model such as a Bayesian network and Markov random fields. So it calculates the marginal distribution for okay, someone is joining. Yeah. So it calculates the marginal distribution for each observed node or variable conditional on any observed nodes or variables. So this is a diagram of the message passing for belief network. So you can see this is a Markov random field. Okay. So Markov random field, yeah, it do two things. Okay, first it will sum the messages and then it will multiply the messages. So how it will sum and multiply the message? You see this example. Okay, so this is the example. So we are interested to know the message passing from B to D. Okay, so B to D, B is directly related to A and C. Okay, because B is connected directly to A, B is connected directly to C, or we can say A and C are the neighbors of B. So we have to see how the message is passing from B to D. So for that we will write this equation, that is message from sender to receiver. S is the sender and T is the receiver. So we can write we are talking about this, that is the message will be passing from B to D, right? B to D. So when the message will be passing from B to D, how we will write it? We will write it by sigma xs, that means sigma of the sender. Okay, sigma of the sender, B is the sender, so that is why sigma of B. Then we will write the potential function of the click of sender and the click of sender and the receivers, that is phi of xb xd. Okay. Okay, someone is joining. Okay. Yeah. So how we will write the message? Message from B to D. B to D will be written as sigma of xb phi, that is potential of xb xd into message from A to B, because B is also receiving message from A, because B is directly related to A and B is directly related to C. B is also related to D, but here when we are talking about message sending, so we do not consider D, because D we have to send the message. So in this step we are not considering D. So we are just talking message from A to B xb and message from C to B xb. Okay. And we will take this message and we will write it as a belief network. So when we will write it as a belief network, here we will also consider D also. Okay, so whenever we are considering D, so here when we are writing as a belief network, not just a message but a belief network, a belief network, what it assumes it is that the message will be message will be passed from neighbors as well as the node receiving the information also. Okay, so here we will write the message from a to b xb, then c to b xb, then this d to b xb. Okay, so this is the equation about belief propagation. Okay, so this is just equation. You just need to know the concept of what is a belief propagation, okay, and how it calculates the marginal distribution. So marginal distribution is calculated by the help of message. So message is calculated in two steps. Okay, so first step, what we will do, we will when we are doing the sigma process, sum product message passing. Okay, so first we will do the sum and then we will do the product. So when we will do the sum of message passing, what we will do, we will not consider the receiver. Okay, we will not consider the receiver, we will consider the other nodes. Okay, so which nodes we will consider? If we want to pass message from b to d, we will consider its neighbor. What is neighbor? A is a neighbor of b, c is a neighbor of b, and d is also a neighbor of b, but d is a sender. So these are receivers. So receiver, we will not consider receiver in this equation. So that is why phi of potential function between this b and d, that is why phi xb xd, and then message from a to b, because it is assumed that a will send some message to b, because a is dependent on b, and then c will also send some message on b, because b is dependent on c also. So that is why message from a to b and message from c to b. But whenever we are writing the second step, that is product of the message, we have to consider all its neighbor. So message from a to b xb, message from c to b xb, and message from d to b xb. Okay, so two step, one is sum and second is products. Whenever we are doing sum, we are not considering the receiver node, but when we are doing product, we are considering all the nodes. Okay, so this is equation about belief propagation. Okay.
Sir, in the belief propagation, we are going to calculate the marginal distribution.
Yeah, yeah,
We are taking both observed and unobserved nodes.
yeah.
Correct, sir?
For unobserved node, we are yeah, 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 yeah.
Ah,
We are taking both the observed as well as unobserved values.
how we
Okay,
are going to identify which node is an observed and which node is
that
unobserved?
will be mentioned to you in your system. Okay, mentioned to you in
Okay,
your question, or mentioned to you in the system.
okay, 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 sir.
So this is about belief propagation. You just see the
Sir,
concept that
sir,
is important.
one
Yeah, yeah,
last doubt.
yeah, yeah,
No, here if you see in the belief propagation, the
yeah,
product is M target to source. That is what it has been written, I suppose. Which means that only the receiver nodes has been made the product. If you see here, A to B,
yeah,
C to B, and then D to B. So here, only what are all the messages is being received
yeah, yeah,
to the B. Only those things has been considered as a product. Is that right? Or we need to consider which is being sent to others also because it is an undirected graph. So
undirected
two-way
graph, that
communication is
means you will
possible.
both send the information as well as receive the information, two-way thing,
Yeah.
right? So in this step, what we are doing, we are basically sending the information, but in the sending process also from b to d, what we are assuming is, as this is related, this b is related to a, and b is related to c, okay, directly related to c. That is why some message will be passing from c to b as well as a to b. So that is why we are considering a as well as we are considering c. Now this is about receiving the message. Okay, sending message we have done, this is about receiving the message. This so when receiving the message, when receiving the message a will be passed to b, this c message will be passed to b, and this d message will be passed to b. So that is why message from a to b, message from c to b, and message from d to b. So this is the
Okay.
receiving characteristic. This is receiving and this is sending. Okay.
Okay. Okay. Okay. Okay.
Oh,
Thanks.
oh. Now okay, someone is joining. Yeah. Now belief propagation in trees. Okay, so yeah, this is a normally a belief propagation. Okay, now we are here in this example, or in this slide. What we are interested. We are interested to have a belief propagation in trees. Okay, so when there is a tree-like structure, and you want to have a belief propagation, what we will do, first step is you will assume any node as its root. Okay, any node as its root node, that you can assume any node. Okay, so whenever you are assuming any node as your root node, so in first step will be sending the information to the root node, and second step is first step is receiving the information to the root node, and second step is sending the information from the root node. So first step, it is to collect the message to the root node. Here this node is considered as a root node. So if graph is tree, any node can be considered as a root node. So according to our belief propagation, what we will do is we will collect all the information from all the nodes to the root node. And second step, when the message is collected, we will distribute back to the leaves. Okay, or we will distribute back to the other nodes apart from the root node, and we will apply this same equation of how here it is written, same equation we can apply. So that is belief propagation in trees. Okay, so guarantee to converge to marginals. Okay, collect, distribute, converges with just one update per message. Okay, so what is happening is we are the message is with just one update per message. So any node will be updated by just one update per message. Okay, so for each edge there are two messages. One when it is the root node is receiving the information, that is one message. Second message is when the root node is distributing the information. Okay, so let's say this is another node. So this node will only be updated when it is receiving the information from the root node. So that is why it is has been written as it collect, distribute, converges with just one update per message. One update per message. That message is the message when it is collecting the information, or when the this root node is distributing the information back to the nodes. So this is in case of belief propagation in tree. But if we have a cyclic loop, or if we have a loopy graph, we don't have tree, and if we have a loopy graph, then this belief propagation gives approximate inference. Okay, here as there is a direct flow of messages from each node to the root node, and from the root node back to each node. So here it is a guarantee to converge to marginal, means you will get the right answer. But if it is a loopy graph, okay, or if it is a cyclic graph or anything like that, so this belief propagation will give a approximate inference. Okay, so this summary: belief propagation passes message between the neighboring nodes. It fuse the incoming message from all neighbors except the receiving node. Okay, so this is the first step. So in the first step, what it will the receiving node, it does not collect the information from the receiving node. So that is what has been told in the second point. And third point: collect evidence and distribute serial order in trees. Exact marginal, that means you will get the exact answer in case of a belief propagation in trees. But when you have a loopy graph, then what will happen is this message keep on iterating, okay, again and again. So that is why it will always converge to an approximate marginal and not the correct marginal. So that is the conclusion of belief propagation when we are applying this on a tree. Okay, so any doubt in this?
Sir, in the belief propagation, at a time we can send only one message. We can't do parallel.
Yeah, parallel we cannot do.
Just only serial. Means
Yeah.
after receiving that message, then only the second node is going to send the message.
Yes.
Means only one message at a time.
Yeah.
Oh,
Yeah, so by this, this is belief propagation. It is all theoretically covered. Okay, so by this we will move on to this topics on which weeknight assignment question are based. First is undirected graphical model, Markov model, and then propagation network. So this is the question first. In the undirected graph given below, how many terms will be there in its potential function factorization? So any guesses for this? Option A is 7, option B 3, option C 5, and option D 9. So any guesses for this?
Nayan.
9, okay. Will clicks have only two nodes? No, it can have more than two nodes, because here it is a whenever we are dealing such question and whenever graphs are very complicated, so what will happen is two nodes, it is difficult to have two nodes, so that is why we take more than two nodes. Okay, so it will be same as maximum number of clicks in the graph. So clicks in the graph, we are for basically forming three clicks, that is AED. Okay, this is a click, then ABCD, this is the click. Okay, and then BCF, this is the click. So we are basically forming three clicks. Okay, more clicks can be formed. Yeah, here if we form this click, so what will happen is if we form this ABC, then what will happen is whenever we are doing connection from A to C, the connection will be disturbed from by another click, that is because this BD is also connected. If this line is not there, then we can convert this click as ABC and ADC. Okay, but whenever we will divide ABCD in a click called ABD, then what will happen is we are disturbing this click. Okay, we are disturbing this edge. Okay, so
So
that is why
that should not be a cross communication, is it? If that is the case,
can you
if
please repeat?
while we are forming a click, we should not consider the cross
No,
communication. I
cross
mean to say.
communication cannot be considered, because
Okay. Okay.
ABC if you will consider, then this AC link, yeah, it is disturbing by this BD link. Okay, so that is
Okay.
why we
Okay.
cannot take ABC. Similarly, we
Okay.
cannot take BCD. Okay, so that is why maximum number of clicks are 3. Okay, is there any other possibility? No, no other possibility, because if we will take AD like ED and AD and this, then what we will take is, yeah, you can take this like ED, okay, AD and ED, then AB, BC, this and this. Okay, yeah, this can be done, but again the problem is, again you have to consider this. Now AC also you have to consider. So yeah, potentially you can have more than 3 clicks, but on a simplified way you can write for 3, maximum number of clicks is 3. So yeah,
Suppose
potentially this can also be a case, right? AE can be a case. Like let's try this.
Yeah,
Okay,
only two nodes. If you are having
yeah,
AE can be, ED
EE
can
can
be,
be known,
AD can be.
this can be done, this can
Yeah,
also
that's
be
what.
done. So 3 are there.
Yeah.
more than
Then this
three,
can
it's
be done,
possible.
this can be done, this can be done, and this can be done. Okay, but then whenever you are the problem here is whenever you will be joining AC and BD. Okay, whenever you will be joining AC, then you have to join this BD also, then this will not make sense. So that is why you have to consider ABCD. Okay, so this is the problem here. And if you consider ABCD, then only remain is this two clicks, AED and BFC. So that is the problem.
Hmm. No, only two nodes can form a click, right?
Yeah, two
Only
nodes
two
can form
nodes.
a click, but see, like
Sir, as
here,
you told, as simple as possible, we have to make the clicks, no, sir. So according to
as
that,
sim,
BF is also make one clip, and that is not any interference is there. No
yeah,
interference is there according to BCF.
Yeah,
BF is we
no
make one click
interference should
and
be there,
BC.
right? Like here, if
Yeah.
I say three no three clicks are there, then I will form one click here, and one click here,
Okay.
and
Then
one click
2,
here.
then BC 1, then
Now
BC.
whenever I am forming this click, because I also have to join this click also, right?
No, sir. Even though if we are not considering that, the
Yeah,
clips more than 3 only.
more than three only. How?
Means if I'm taking this upper that triangle, that AED.
Yeah,
Yes, sir.
AED. Yeah, yeah,
So remove that everything, sir.
yeah, yeah.
In this, if I'm talking about the AED, if I'm
AED.
consider 3 nodes, then we can make it as a one click.
Yeah,
One click.
yeah.
So if I'm talking about a 2, then AE is also making 1. Then ED is also making 1. There is no interference between these nodes.
Yeah, yeah, that is true. That is true.
Yeah.
Okay, okay. So you are
Because
telling
in
to
the assignment, one
telling
more
to divide
option.
AED with AE and ED.
Because
Like
as
B,
you told,
yeah, yeah.
as simple as
Like
possible, we
yeah,
can
yeah.
make.
Like
Uh,
BCF, you are
uh,
telling to consider
yeah, there
yeah,
is no
BF and
restrictions among the
CF.
nodes.
Yeah, yeah. That can be done. So by
Yeah.
that, how many possible cases are there? By
Then
that,
one, two, three.
five
5,
Mm,
cases are
5.
there, right?
Yeah.
Five cases are there. AED, if I divide, then AE and this,
Sita.
okay, and then BF and CF, right, and then ABCD. So that
But
is
which
that is
is
five.
preferable, sir? 5 or 3? Which
See,
is a
whenever
preferred
you are
way?
doing calculation, 5 is more preferable, because
Okay.
factorization, that is the concept of factorization, right? The
This
mostly,
terms is, yeah, terms is as similar as factorization, is it?
yeah,
That
yeah,
is what
yeah,
we mean.
yeah, yeah,
Okay.
yeah. But here you don't want to do the interference, because whenever you will divide the ABCD click, so here the problem is you will face this interference. So that is why ABCD you cannot break, according to me. So yeah, 5 can be the correct answer.
Sir, not 5, sir. According to this, it will be 6 only.
6, 1, 2,
Yeah.
3, 4.
See, A to E is a 1. Then E to D is a 1. Then enter we can make as a 1, like 3. Similarly, B to F is a 1. Then C to F is a 1. Then enter make it as a 3. 3 plus 3, it's 6 only. How come
So
it's 5?
you want to make A and D.
Sir, remove everything, sir.
Yeah, yeah. Now tell
Okay,
me.
A to E is a 1.
A2 is a 1, okay.
Then E to D is a 1.
Yeah, 2.
Then enter AED, we can make it as a 1.
AED no, no, no. That you cannot take. No, you have
We
already
can't.
factorized AED. Now how you can
Okay.
again take AED again?
Okay, okay. Then it's a 5.
Yeah.
It,
So
is it like that, sir?
hello.
Or we can make AE and AD as 2. Either of this we can make it, is it? Is it
AE
like
and
that?
AD. AE and AD. AD you
No,
cannot
no.
make, na.
No,
AD if you
AE and ED.
yeah, yeah, AE and ED you can make, then BF and
Uh,
CF you can make, and then this completely ABCD you can make. Here all the connection
so,
are there, here all of the connection are happening, here all the connection are happening. So 5 can be answered. Okay?
Yes, sir. 5 will be the answer.
Yeah. So yeah, it is written as B here, so you can correct it, can make it C. Okay? Okay. So let me, is it clear to everyone how we are making the clicks? Clear, right? Okay. So here consider the Markov network shown in the figure. Which of the following is not Markov blanket of 4? Markov blanket means all the neighbors. Okay, a Markov blanket consists of all the neighbors of the variable. So which of the following node is not a Markov blanket of 4? So any guesses for this? Yeah, it is a very simple question.
Sir, 5.
5. Anything else? Only 5? Okay, let me see. Yeah, 4. 1 is a neighbor, so this is which of the following is not in a Markov blanket? Yeah, so 1 is not in a Markov blanket. Then 3. 3 is not in a Markov blanket. 3 is not given in the question. 6 is not in the Markov blanket. Okay. Then 2 is not in the Markov blanket. 8 is not in the Markov blanket. 7 is also not in the Markov blanket, right?
Yes, yes,
Yeah,
yes.
7 is not in the Markov blanket. 4 we cannot say anything about 4. So 5 and 7 is not in the Markov blanket of 4. Okay, so D as well as G is the correct answer. Okay, so any guesses, any doubt regarding this question? What is a Markov blanket? This is very important. So what does the Markov rules say is that if the Markov blanket is given, then other nodes are independent of that node of that Markov blanket. Okay.
Markov blanket is the neighboring nodes, is it?
The neighboring nodes of that variable.
Okay, fine.
Okay. Now move on to the question number 3. Consider the Markov random field which node has have the largest Markov blanket, that is Markov blanket with the most number of nodes. Okay, one or more option can be correct. Okay, so which node has the largest Markov blanket? Okay, so let's say A. What are the neighbors of A? F is the neighbor of A, E is the neighbor of A, B is the neighbor of A, and C is the neighbor of A. So A has 4 nodes in the blanket. Okay, now about B. B has yeah, 1 2 1 2 only. Okay, B has 2 nodes. C has 1 2 3 4. C has also 4. D
One,
D has only 1. E has
three,
only one,
three,
two, three. Yeah, E has 3. F
two,
F has 2. F has 2. So what is the correct answer? Largest Markov blanket. Okay. What is the correct answer? A as well as D. Okay, A as well as D is the correct answer. A as well as sorry,
C.
sorry, C. A
So
as well
we
as
need to consider only the immediate neighbors, is it? For
yeah.
the okay.
Markov blanket means immediate neighbor only. Okay. A as well as C has 4 nodes, that is maximum, so that is why A and C is your correct answer. Okay, is it clear to everyone? Okay, I think it is clear. Okay, any doubt?
Okay.
Okay, so consider the Bayesian network given below. Which of the following independency relation hold? A and B are independent if C is given. A and B are independent if C is given. True or false?
True.
True or false?
Dependent, right? A and B are dependent
Yeah,
with
yeah.
respect to
So this
basic.
is
Yes.
false, right? This is the explaining away effect of the third rule. Okay, third rule. What it tell is, if the child is given, then the parents are dependent. Okay, so that is why this is false. Now A and B are independent if no other variables are given. No other variables are given. If no other variables are given, then A and B are independent. Yeah, that is true. Okay, if C and D are not independent if A is given. C and D, okay, C and D are not independent if A is given. If A is given, then C and D are independent. So this is again false, right? A and F are independent if C is given. A and F are independent if C is given. This is also true. So B as well as D is your correct answer. Okay, so any doubt? Any doubt in this? This is basically related to your Bayesian net. So Bayesian net, we have 3 rules, right? One is this: A, B, C. So in this rule, if B is given, then A and C are dependent or independent? Independent, right? So second rule, A. Yeah, second rule is A, B, and C. B is a parent of both A and C. So if B is given, then A and C are independent. Now this is the third rule, that is explaining away effect, right? A and C. If A and C are the parents, if A and C are the here what will happen is, if B is given, then A and C are dependent, right? So these are the three rules. So according to the three rules, I have solved the question. So this is independent, this is independent, and this is dependent. So these are the three rules you have to keep in mind. Okay. This three rules is also discussed in today's lecture also. Yeah. You see this three example, right? This is the example, this is the example, okay, and this is the example. Okay, so this example, what we have seen, this example, if B is given, then A and C are independent. Here if A is given, B and C are independent, but here if C is given, then A and B are dependent. So these are the three rules for the Bayesian network. Okay, so any doubt in this? Okay. So let me move to the next question. Okay, in the Bayesian network, from question number 4, assume that variable is binary. What is the equivalent? What is the number of independent parameter required to represent all the probability table for the distribution? Okay, so this is the Bayesian network that is given in the previous question. So we have to find out the number of independent parameters required to represent all the probability tables for the distribution. Okay, so we will start from this two node, right? About this node we will take the marginal probability. This node also we will take the marginal probability. Now this node we will take the conditional probability with respect to A. This node we will take the conditional probability with respect to A. Now this node C, we cannot take the marginal probability, but we have to take conditional probability with respect to B. Now about this two node we will take the conditional probability with respect to C. We will F, we will take the conditional probability with respect to C. Okay, is this clear? Again I am repeating, for this A and B, as these are the root nodes, we will take the marginal probability, that is we will write PA and we will write PB. Okay, now for this node PD, we will write conditional probability with respect to its parent. So what is its parent? Its parent is A. So we will write PD given A. Now about C, again same thing, we will write probability of C given A, and C has two parents, so that is the probability of C given A and B. Okay, now about E, we will again write for C, C we have discussed. For E, we will take the conditional probability with respect to C. For F, again we will take the conditional probability with respect to C. Okay, so these are the cases. Now let's form the table one by one for PA. So whenever we will form the table for PA, we will have only one thing. Okay, we will have only one value, right? PA is equal to something. Similarly for PB also we will have one value, that is PB will be equal to something. Okay, now for PC, given AB, that is this case C, because C has two parents, right? A as well as B. For C given AB, we will have four cases, right? When A equals to 0, B equals to 0, when A equals to 0, B equals to 1, when A equals to 1, B equals to 0, and when A equals to 1, B equals to 1. So that is why for this PC given AB, we will have four cases. Now for this PD given A, we will have two cases, that is PD given A equals to 0, PD given A equals to 1. So that means two cases. For E and F also we will have two cases, that is C given 0 and C given 1. So how many cases we will have for PA? This we will have one case. Okay, this will have one case. For PB we will have one case. For this D given A, we will have two cases. Okay, PD given A, we will have two cases. Okay, now PC given AB, PC given AB, A and B, we will have four cases, right? we will have 4 cases. Now last thing, that is PE given C and PF given C. So PE given C, we will have 2 cases, and PF given C, we will have 2 cases. So how many cases in total? 1 plus 1 2, 2 plus 2 4, 4 plus 4 8, 8 plus 2 10, 10 plus 2 12. So option B is your correct answer. Okay, so any doubt regarding this? Should I again repeat?
Yes, sir. Please repeat.
Okay. Yeah, so see this graph. Okay, you can see this graph. This is a graph of Bayesian network. So Bayesian network, what we will know is probability of x1 x2 dot 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 xn will be equal to pi of xi probability of p of xi probability of p of x x of parent. Okay, so that means parent of xi. Is this clear? Okay, so what we were
So you are
interested.
not sharing the right screen, sir.
Yeah, please repeat.
No, you are not sharing the screen that you are working.
Screen is not shared. Okay, how it happened? It is
Shared,
shared,
sir.
I think.
Sir, yes, sir, shared.
Shared, right? Okay. Okay, so this is the thing, that probability of x1 x2 dot 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 xn will be equal to multiplication of probability of xi with respect to its parent. So that is Bayesian network. Okay, so this we have to apply. So for applying this, we have to have the cases. Last lecture, if you will remember, so please check that burglary and earthquake question. There you will find everything. Okay, so let's see here. So for A and B are your root nodes. So A and B will have only marginal probability, that is PA and PB. It is not dependent on anything, so that is why PA and PB. So is it clear? A and B are your root node, that is why marginal probability. Clear, right?
Yes, sir.
Okay. Now what about
Yes, sir.
D? D will have conditional probability because it has parent A, right? So that is why D given A. Clear? For D, it
Yes,
is
sir.
clear, right? Now, what about C? C has two parents, that is A and B. So that is why C given A comma B. Clear, right? Now, what about E and F? Probability of E has one parent, that is C. That is why probability of E given C. Similarly, probability of F
F.
given C. Clear? So this all we have to multiply to have the probability of the system. Okay, clear, right? Up to this it is clear, right?
Yes, sir.
No doubt, right? Okay, so here it is has been
No,
told
sir.
how many
Yes, sir.
parameters you have to how many parameters you have to have to calculate this probability. So if this is a marginal probability, we have only one parameter because PA will have one value. Similarly, PB will have one value. Okay, so PA we have one value, PB we have one value. Any doubt? Because there will be something PA equals to something, PB equals to something, right? So that is why PA we have one value, PB we have one value. Clear, right?
Yes, sir.
Yeah. Now when we are having D given A, so you will have to make a table. So how we will make a table? You will have, sorry, D we are calculating, right? Probability of D we are calculating. So D we have to make a table. What table we will make? We will have two cases. Okay, we will have two cases. One is as D is dependent on A, so we will have one case as A equals to 0, and we will have second case as A equals to 1. That means you can say when A is there or A is not there, that is A bar, or when A is there, that is A. So we will have two cases. So for this we will have two cases. Is it clear? Because D depends on A, and A will have two cases. Either will it happen or it will not happen. So that is why we will require two cases. That is PD when A equals to 0 and PD when A equals to 1. So that is why two cases. Okay, so that is why I have written 2. Is it clear? Clear, right?
Yes, sir.
Yeah. Now what about
Yes, sir.
C given AB? C given AB when we will write. So C we have to find out, and given AB, then there will be cases for A and B. 4 cases of A and B. AB, 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 and let's say AB. Okay. First case is both are 0. Okay, both are 0. This is 0 and this is also 0. First case. Second is this is 1, this is 0. Second is this is 0 and this is 1, and this is 0 0 1 1. Okay, so 0 0 1 0 0 1 and 1 1. So there are 4 cases when we are calculating PC given A and B. So that is why here we have 4 cases. Now here it is similar to D given A. So here we will have 2 cases, here we will have 2 cases. So how many parameters total? 1 plus 1, that is 2, 2 plus 2, that is 4, 4 plus 4, that is 8, 8 plus 2 10, 10 plus 2 12. So 12 will be your correct answer. Okay, is it clear?
Yes, yes, sir.
Okay. Now in an undirected graph given below, which nodes are conditionally independent of each other given B? So given B, which two nodes are conditionally independent? So what we have to do, we have to see if the path can be traveled or not. If it is blocked, so path cannot be traveled and it is independent. If it is not blocked, then path can be traveled and it is dependent. So let's talk about A and D. Where is A? This is your A and this is your D, and we have to block B. That means we are blocking B. So if we block B, then also this path can be traveled, A to C, C to E, and E to D. That means path can be traveled. So that is why A and D are independent. A and D are not independent. Okay, A and D are not independent. So this is false. A and D are dependent because path can be traveled. Okay, now D and E. D and E, where is D? This is D and this is E. D and E, it is dependent. It is directly dependent. So that is why this is also false. Now C and D, C and D, C and D, C and D. Yeah, C and D, again the path can be traveled. C E D. So again this is false. AF, AF, AF. Again the path can be traveled. This is false. And none of the above. So none of the above should be true. Okay, so option E is the correct answer. All pairs have alternate route to each other that does not pass through B. So that is why all are conditionally dependent. Okay, if we block B also, all are conditionally dependent. So that is why A, B, C and D all are incorrect answer. Okay, so E is the correct answer. Okay, so any doubt in this?
Sir, A to F, tell me, sir, once again.
A to F, A to F, yeah, this is the route. A to F, A to C, then C to F. This is the path. Okay,
So how we traverse D, sir, even though we have path between A to F?
traverse to D.
Ah,
Why we need to traverse to D? This is the example you are talking about, right? A to F.
ah, ah,
So
ah.
here you go from A to C, then C
Okay.
to F. This is the path we will take.
Mm-hmm. Okay, sir.
So others are clear, right? CD, let's see CD, CD, this is the part. Okay, this is the part, CD. Okay, okay, let me erase this. Yeah, so this is for CD, C to E, then E to D. Okay, now let me erase this for DE. For DE, if you will tell DE, DE. Okay, DE, where is the DE? So this is the path. So this can also be traversed. So again, this is dependent. Now last thing is AD. AD, you have to go from A to C, C to E, C to E. So this is the path. Okay, this is the path. A C E D. So again, this is dependent. Okay, so that is why all are false. All are dependent. Okay, all the cases are dependent. AD is also dependent, D is also dependent, CD is also dependent, AF is also dependent. So option E is the correct answer. Okay, no doubt, right?
Yes.
Okay, so question number 7, one or more correct option. Okay, consider the MRF given below. Which of the following factorizations of P A B C D E satisfy the independence assumption represented by this MRF? Okay, so that is how you can factorize this. That is P A B C D E 1 by Z phi 1 of A B C D and phi 2 B E, then this phi 1 B phi 2 A C D, and then phi 3 A B E, then A B C D E phi 1 A B D E C D D phi 1 A B, okay, A B C D C D, and then B D E. Okay, so any guesses? Yeah, let's take the first thing, that is A B C D and B E. That is true. This is true. Now A B C D phi 1 B, okay, then A C D A C D, then A B E A B E. Okay, again B B can be a click. Okay, B can be a click. Then A C D and A B E. This is false. Then phi
There is
3.
an interference, sir, so we can't travel ACD, right?
Yeah, ACD we cannot travel. That is why this is false.
Yeah.
Now
Okay.
A B C D E A B D E A B D E A B D, then E. E, there is no link, right? A B D E, how it is traveling. So again this is false. Now A B A B C D, okay, and B D E or D B E. D B, yeah, but again it is not covering this link. That is this AD link. It is not covering. So again this is false. So according to me, A is the correct answer. Okay, yeah, A is the correct answer. So is it clear?
Yes.
Which of the following best describe the Markov property, the hidden Markov model? Okay, the future state depends on the current state and the entire past sequence of states. Okay, the future state depends only on the current state and is independent of the past state given the current state. Okay, the future state on the past depends on the past state. Okay, and the future state depend on the past state and future state given the current state. So this is of course for the future state depends only on the past state. Okay, and independent of the current state. Okay, so let's make this node, B is the node and C is the node. This is a past node. Okay, this is a current node, this is a future node. Okay, the future state depends on the current state and the entire past sequence of state. The future state C depends on the current state and the entire past sequence of states. Okay, yeah, it can depend. According to me, it can depend. If nothing is given, it can depend. The future state depends only on the current state. Future state only depend on the and is independent of the past state given the current state. So if this is given, then A and C are independent. So of course this is true. Okay, the future state depends on the past state. This is false. The future state depends only on the past state. That means C depends only on A and is independent of the current state. So this is also false. Now what about this? A future state depends on the current state. The future state C depends on the current state, that is B, okay, and current state and entire past sequence of state. So if nothing is given, then it can depend. We cannot tell. if nothing is given, right? Here it is nothing is given. So according to me, A is also correct. Okay, because nothing is given here. So according to me, A is also correct as well as B. Okay. So is it clear why I am telling A also, because nothing is given here. So as nothing is given, so it can depend on the past sequence also. But if the current state is given, then it cannot depend on the past state. So is it clear? This is the past state, this is the current state, and this is the future state. So is it clear? According to me, A is also correct. Okay. If nothing is given, then A is also correct. But B, if only one option is correct, then yeah, go for B only. But if more than one option is correct, then A is also true. Okay. So is it clear to all of you?
Yes, sir.
Clear, right?
Yes, sir.
Yes. Yes.
Okay. What is the main objective of belief propagation in a graphical model? To compute the shortest path between two nodes. Okay. To calculate the marginal probability for each node. Okay. To find the maximum likelihood path in a graph, and D, to determine the posterior distribution of the hidden variable.
B, sir. Marginal
Yeah.
probabilities.
So B, this is a theoretical question. So the main objective of belief network is to calculate the marginal probability for each node. Okay. According to the dependence and exchanging of message between the neighboring nodes, it will just exchange information and it will try to calculate the marginal probability for each node. If it is a tree, definitely it will calculate. If it is a loopy structure, then approximately it will calculate, but approximately it will calculate. It will not calculate the true value. That is why B is a correct answer. Okay. Now we are on to our last question, that is question number 10. In the Markov network given in the figure, two students make the following claim. Manish claims variable 1, okay, is dependent on variable 7 given 2. Okay. Trina claims that variable 2, okay, where is the variable 2, is independent of variable 6 given 3. Okay, given 3. So let's first take the claim of Manish, that is given variable 2. That means he is blocking the second variable. Now he is telling one is dependent on variable 7. One is dependent on variable 7. So is one is dependent. If we block 2, can we reach 7? Mm, we cannot reach 7, right?
No, sir.
We cannot reach 7. So Manish is incorrect, right? Because he is telling it is
Yeah.
dependent. But as we cannot reach 7, if we block 2,
It
so
is
it is
different.
independent. So this is a false statement. Okay. Now what about Trina? Let me erase this. Yeah. So what about Trina? Trina is 6 is given. So 6 is given. So let's block 6. Yeah, 6 is given. Trina claims that 2 is independent of 6. Okay, 2 is independent of 6. 2 is independent of 6. Okay, 3 is given. Sorry. Okay, 3 is given. Given is 3. Okay, given is 3. That means 3 is blocked. So 2 is independent of 6 given variable 3. So can we reach 6 even if 3 is given? Yes, we can reach 6 via 4. This is the path. If this path we will follow, we can reach 6. So that means 2 and 6 are
Independent.
dependent. So again, this is a false statement. So both students are correct. False. Trina is incorrect. Manish is correct. False. Trina is correct. Manish is incorrect. False. Both students are incorrect. True. So option D is the correct answer. Insufficient information, no. Sufficient information. So option D is the correct answer. So is it clear?
Yes, sir.
Clear, right? This question is clear to all of you, right?
Yes, sir. Yes, sir.
Okay, so by this I am ending the session for today. I hope this Markov property, at least this is clear to all of you. Okay, and how the relationship, how the nodes are related to each other in a random Markov field. Previously, we have seen how the nodes are related mainly in case of Bayesian network, but here we have seen how this nodes are related in case of this random Markov field. Okay. Okay, so by this I am ending the session for today. Okay, no doubt, right?
Yes, sir.
Okay,
Thank you, sir.
okay,
Thank you, sir.
Thank you,
okay.
sir.